plot. So it plots alongside the entropy. So you can see that the entropy of English text, and it corresponds with the line at the same level, is about 4.2, something like that, 0 to 8 bytes, 8 being the most random or most unpredictable. And then bitmaps. So bitmaps can exist on a file, although they're uncommon. Typically, they're compressed. Importantly, though, they can exist in memory. And when a program loads a compressed file in the memory, typically it decompresses it. And we've looked at memory dumps and things like that, and you can see the bitmaps residing in there. Now, the problem with bitmaps is that where text is a very tight knot of what you could expect statistically. Bitmaps can be anything. You could have a bitmap of white noise, or you could have a bitmap of a black square. So when you're doing this, though, common bitmaps, and that's where we have to go to commonly, what will you run into? Those show, those stand out. Yes?
Will that work with steganography?
We have a steganography example in here. I would say it'll work with some. Right? There's some very, certain naive, the example we have flips lower bits, least significant bits, that shows up. But there's some very subtle techniques in current steg. Sure. Okay, so the top right is a bitmap. Now that's not looking at it with an image viewer, that's looking at it as a byte plot. So because the window, the byte plot doesn't exactly represent, it's not an image viewer, it's looking at the raw bytes in the file. That's what it'll look like, or it can. That's the histogram for that particular bitmap. But the digraphs, particularly in normal photographs, normal images, will often look like fireworks in the digraph.
And you can see the structure, which is very different from what it was in case of the text. Even if this were SOR encoded or shifted in some way, the picture would look the same. It would just shift around in that view. And that is the power of a simple visualization primitive. So that's your, antique lens number one.
So here we're looking at 3. The bottom left corner, if I get it right, you can start kind of seeing it. So the bottom, this on the here, this part is the digraph view. Off here to this side is the entropy view. Yes.
On the entropy view, how did you scale that vertically? You get 1 entropy reading for the entire file.
It's 1 entropy reading per line. So, and right now it's fixed to the default. So here, it comes out at 640 by 480 in the byte plot view. So each line of this byte plot equates to the location of the entropy. Yep. If you resize this, the byte plot view, the entropy doesn't resize along with it.
Yeah. For entropy, you need a distribution. So you just decide on the window in which you take that distribution.
And yeah, I mean, there are many ways you could do it. You can add tuning knobs to all of these things. But then as you go through the file, you can see that this, the changes as you go. Okay. And again, this is just one example. But what we found, we've looked at a lot of examples, and what we're showing you are things that we've seen appear time and time again. So we're not suggesting these weird one-off examples, unless we tell you it's a weird one-off example. Yeah. Here's a weird one-off example. To the left is to the left is a picture, and inside that picture, in the 2 least significant bytes, is another picture. All right, so of a cat, and all cats are named Mr. Jingles, so that's Mr. Jingles. And here's the view. So what do you notice about it? Actually, let me make it bigger. Okay, you can see something weird going on here. So for the person who asked the steg question, manipulating lower order bits, if you've got 2 levels of things, yeah, it may very well show up. It depends how much you're putting in there and how similar the things are, but you've got a good chance.
Yeah, so it's a familiar beak, but it also is something else. It can probably open beer bottles.
And there's but there's many different image formats. So there's a great deal of depth as you think through this of ways images can be, if you want to identify them programmatically, for example, or try to, there's different ways they're encoded. So you have to think those through. Audio is another good example. Again, it can be compressed, but it has to be uncompressed at some point to actually typically be used. So here's an example. This is a WAV file. Notice the U-shaped, the very distinct high and low bytes for a WAV file. And this is a 44 kilohertz, 16-bit per channel PCM encoded audio. And here, the digraph's very distinct. And this is Sweet Home Alabama. And sadly, when you press the play button on this, it doesn't actually play the song. Okay, so you can see there is structure. It's a different structure. You know, you're not going to get a picture emerge. And then the entropy does change. But I'm going to hit play here. And actually, I'll probably speed this up. See? It changes pretty significantly as you go through. So the idea is, with these insights, how can you programmatically identify these things? Now we know the digraph has that characteristic. And you can see the entropy as well. Now, these are pure fragments, so we're not looking at mix. We're looking at individual primitive types here, essentially.
But you could take a sample out of a larger file and quickly categorize those samples, even if the file were, for example, XORed.
Yes, or the BinViz tool will allow you can just slide to that offset and take a look. Compressed audio, and this is a theme you're going to see again and again. Compressed audio and encrypted and random numbers typically exhibit very little structure as they're intended. But if you think about the nature of each of those categories, compression typically wants to be reversed, right? It's a reversible process. Encryption wasn't designed to be a random number generator, so there are perhaps some statistical characteristics that distinguish it from random numbers themselves. And just taking a look at this MP3, there is some structure there. And looking at it, and this is a view I just want to touch on briefly. It's Dan Kaminsky used it. It's called the dot plot. The link to the original paper, and then Dan Kaminsky's talk there. But the basic idea is it's a measure of self-similarity, a measure of structure within a file. And if you take a sequence of values, byte values or words, here to be or not to be, and you plot them on the horizontal and vertical axes, where they coincide, where 2 appears in, the same word appears on both axes, you plot a point. That's the basic idea.
So just like the digraphs are a measure of bigrams, this is a measure of self-similarity.
And this is the MP3. And you see there is structure in there. You might not notice it with eye. You almost certainly won't recognize it with a hex editor, or you might not. So anyway, these are just, again, once you've found that, you say, well, what caused that? And you can kind of narrow it down and then maybe find a way to use that to your advantage. Video is essentially sequence, uncompressed video, full-frame video, just is the AVI format's just image after image, like a flip book. Compressed images often will have a keyframe, which is a full frame, and then followed by some sequence of frames that just show the difference, followed by the keyframe. So this is just looking inside a compressed AVI. And again, it's useful to see these pictures, so as you're looking at these things, you can't really tell this from a hex editor. Windows PE file. Now this, we won't say it's the same primitive type in there. I mean, if you look at the text region, at the bottom there's a table of strings, so mixed with the code at the top. So the text at the top is what code looks like typically, and then in the resource section, our SRC section has bitmaps and other different types of structure embedded. So but it's useful to. I thought it'd be interesting to actually see what the sections looked like, because you spend a lot of your time in those sections, and then looking at this command.exe as well. So now looking specifically at machine code, we looked at a lot, and we have some statistical analyses at the end. This is just one example. But you get a histogram or a digraph plot that looks kind of like a grid. So if you're going through this file and you see that grid appear, that tells you that it may be machine code, because we found that there's not all that many common primitive types out there that once you get a handle of what they look like, you can start identifying them on the fly. So this is the ever-popular calc.exe, probably the most analyzed program in the world. Okay, so at the top, so as we play this, note, so this is the grid that I was discussing. You'll see that grid, and this top part, the top half of the file is essentially all grid. And you can see that's what it looks like. And then as you transition, you'll see it popped briefly when it hit strings.
Yeah, by the way, you just saw a piece of text, which is the
right there.
Which
so
is your string table.
That's the string table. And then you get into the images that look like fireworks. Right, so you get the fireworks kind of at the end. And this is, as we said, bitmaps could be anything. Data structures, typically you know them when you see them. Oftentimes there'll be blanks. They have a great deal of structure, pardon the pun, but they're visually very recognizable, but they could theoretically contain random numbers. So they but in common practice, they look like this. So what are the statistical signatures like? Is there a way that you can pull out data structures? And as you'll note that we're not talking about knowing a priori the file format in advance. We're not assuming any knowledge. You could combine that with certain knowledge if you know a file format, what should be expected at a given spot, but we're not assuming that. And again, random numbers look like random numbers. The flip side of random numbers, padding, repeating values, and the like are again very easy. But you do see that, so we included that in our thinking about this problem. And then there's the idea of transformation. So we've largely looked at the base primitive types, but they can undergo many, many transformations. Some encryption, compression, and coding being the most common. And if you think about an image on a camera may be an uncompressed image, a TIFF file or something like that. And you load it onto your computer, you load it into Image Editor, you edit it, you save it as a compressed version. That compressed version may be sent over a protocol that uses encoding, text encoding. So these transformations occur. When that compressed image is loaded into memory, it's uncompressed. So one thing we'll like at different points in this game will be different. But oftentimes you can find some signatures will often pop through. So this is just a Windows PE file that's base 64 encoded, and you can see the text region at the top still is visible. And also the vertical lines there, you see that as a common artifact within base 64 encoded files. Sometimes other artifacts like this chunk here, I drew diagonal lines on the top and then there's a mirror image on the bottom, that there may be artifacts in there that you didn't know and that you can use to your advantage. This is a UPX file, I think a compressed file, I think it's cmd.exe. And at the top though, by default it only compressed the code region and the other structures there. So you can see a kind of certain times structure pops through.
And this code would not look like the code in the byte plot.
Yeah, it would look like a compressed, more like the white noise, the Starfield kind of look. And then encrypted looks a lot like random. And then it's also useful to think in terms of the obfuscation techniques people will do within their code. And there's a wide variety people can use. We've chosen just a couple of examples to illustrate. If you, adding and subtracting a constant, looking at a hex editor, things will look different, right? But other properties shine through with the right magnifying glass, the right window. So here's one that we've shifted each by 150 and wrapped around if it exceeded 255.